Welcome back to C23 Classroom channel. So we continue our discussion about boundary layer. So today I would like to share with you another two terms from boundary layer that you need to understand, which is the displacement thickness, delta star, and the momentum thickness. Displacement thickness is shown by delta and the asterisk mark here. Normally we could say it is delta star. So the definition of displacement thickness is the distance the surface would have to move in the y direction to reduce the flow passing by a volume equivalent to the real effect of boundary layers. So in this syllabus, we are focusing on flow which is incompressible flow. So you might have textbook that discuss about the compressible flow and its boundary layer problems. So to simplify this definition, it is actually because to make sure that our calculation will follow or will fulfill the conservation of mass. Please look into this diagram. We have a thin flat plate like this, and then we have capital U, which show the free stream velocity, and then once it's hit the flat plate here, the no slip condition occur and will create velocity distribution like this. Okay, through this diagram, we could say that a rectangular area is now transformed itself to a distribution area like this. So the area of this one, mass of the inlet, must be equal to the mass at the outlet at here. Because the area here is not the same, we could say that the conservation of mass is not fulfilled yet. What we need to do is the balance to balance the mass here, we need to add an extra area here. So at the top of this area, the velocity is already reached the velocity of free stream velocity. So we mark this velocity as capital U. And then we need to increase a little bit to make sure that the total mass at outlet here must be equal to the total mass at the inlet. So we give a definition. The height of this one is the displacement thickness. Because this idea is using the conservation of mass, first we need to determine what is the equation to calculate the mass. As we know, density is mass over volume. Then we could say that mass can be defined as density times volume. And this volume can be calculated directly from this diagram. So which is, it is length times its height and times its width. So from this diagram, we could say that the length is capital U, the height is delta, because according to this diagram, we could say that the local velocity here is actually already reached 99% from the free stream velocity. So means this height is boundary layer thickness. So we take boundary layer thickness as its height. And then to simplify our calculation, we only focus on the 2D, which is x-axis and y-axis. So we assume that its width is only 1 unit. So we could say that mass can be calculated by multiplying rho, u, and delta. According to this diagram, we could say that total mass from A area here must be equal to the total mass of B and C. So we could write an equation of mass A is equal to mass B plus mass C. For mass for A and mass for C is easy to calculate because the area is rectangular. We could say that mass for A is rho, capital U and delta, and mass for C is rho, U and delta star. So we have a little bit problem to define about the mass in area B. So the answer for that one is the integral from 0 to delta rho small u and dy is the total mass of area B. So if we look at this area, so the local velocity keep increasing. So what we need to do is we just imagine we have a colored area of this one. So because it is very small, we could imagine that this area is a rectangular area. So we define that its length is small u, which is the local velocity. The thickness of this one is very small, so we define it as dy. So the mass only for the colored area here is rho, u, and dy. So to find what is the total mass in this curved area, we could integrate the value of this one. That's why for this equation, we could say that rho u dy is actually only the mass for the colored area. Then we integrate this term from 0 to delta, we will get the total mass for B area. After that, because we want to define what is delta star, we rearrange this equation into this one. Then we simplify it into this, and finally we could say that this is the final term of delta star. As a conclusion, we could say that the equation for displacement thickness is delta star equal integral from 0 to delta 1 minus u over u dy, which is delta star is the displacement thickness, delta is the boundary layer thickness, u is the local velocity, and capital U is free stream velocity. So please be careful when you write U and capital U. Please differentiate your writing method to make sure that examiners will understand that you are writing small u and capital U. Thank you for watching. Please subscribe this channel, C23 Classroom channel. Thank you for watching.